Welcome. I'm Jim Laris in MSR. This is the second in the series of talks on Midori. Those of you who missed the first one, it's on ResNet, and it's the general overview that Joe Duffy gave. We're now going to have much more targeted talks on a fairly regular series. I guess Jinsong was saying that there's a whole list of people that have signed up to give talks on their parts of Midori, and so we'll start scheduling them. I think this is probably a reasonable format, the lunchtime, bring your own lunch type thing. If you have particular feedback or comments, you should send it to me. But the hope is that the Midori team is now ready to talk about what they've done. They're looking for collaboration and looking for people to use Midori. And so the talks will provide an accessible overview and a point of contact for people to contact if they want to get going on this. So without further ado, I'll give the platform over to Jinsong and thank him for coming in, giving us a talk on this.
Can you hear me? Okay. So what I'm going to talk about today is the I/O path and how we manage data in Midori platform. Like James said, there will be a series of talks. Midori is a crazy project. We build a kernel, we build network stack, UI stack, storage stack, new programming model, new application model. There's a lot of new and exciting stuff. So this is the first deep drill. There will be other deep drills. We will try to keep once a month cadence going forward. So look for announcement and welcome to the series. If you have questions, just interrupt. I like to make this interactive instead of waiting everything toward the end. So the first thing about Midori you want to know is it's really a microkernel architecture in the sense that there is no device driver running in kernel. All right, all device drivers and all I/O-related services are running in user mode processes. Disk driver, that's a user mode process. Network driver, that's a user mode process. File system, that's a user mode process. There is no code in kernel doing I/O. So what does kernel do? Kernel is really, really simple. At the end of the day, kernel manage CPU scheduling. It manages the memory allocations. It manages the lifetime of the processes. And it helps in the inter-process communication. Nothing else, right? There's no paging. There's no I/O, nothing. And another very, very important thing you will see recurring scheme in the talks is the software isolated processes concept. So Midori has a very deep root in singularity. So the software isolated process, this concept was really introduced by Singularity, and we love it, and we kept it, and it is a core of the Midori principles. So what are software isolated processes? It basically says multiple processes can live in the same hardware address space, right? So how do you isolate them? Well, the answer is managed code. It's type safety and memory safety. If you're not allowed to write unsafe code, then for the merit of type safety, you can actually isolate the processes even though they coexist in the same hardware address space. So I look at hardware isolated versus software isolated in such a picture. In Windows and Linux, the traditional processes are hardware isolated. The processor hardware actually have the page table for different process and therefore different address space. And on the surface, you look at that and you say, aha, that's very, very strong isolation. But guess what? Performance really sucks in that picture when you switch between processes. So what do people do? They have very strong isolation. There's a thick wall in between. And people say, I can't live with the performance. Let's punch some holes in the wall, right? So both Linux windows, you see the read-write shared memory. There are huge holes between the wall. Regardless how thick the wall is, once you have holes, the isolation starts to disappear. Yeah, go ahead.
So all the domains share the single address space, right? But from the specification, does domains have the whole view of the whole? I mean, because it's a fact, whether you need, when you change the address space, do you need to hold log and make all of domains to know the address space is changed or not?
So the question is, when we switch address spaces, does the kernel need to notify all the processes about the change?
Does the kernel need to tell the process who share the single address space?
Right.
Or not?
So the answer is no. When you switch address space, it is preemptive action. It's not a cooperative action. You don't need to cooperative with all the processes living in the address space. Say, I want to switch address space. Is that okay with you? There's no such thing, right? You want to switch, you switch. The processes don't know.
No. I mean, when you touch the address space, right? Like for example, in the process share the same address space, right?
Right.
So if you change, like in Linux, if you like multiple threads share the same address space and they do have the same view, and when you change the address space mapping, you have to because all threads have the same view, so you have to update. You have to make all threads know the address space is changed, right? Here
Okay.
is better for the same. You can say the process in domain have share the same address space, right? But when you, for example, when you create one more process, and I assume you're going to touch the address space, right? When you touch the address space, do you need to follow all of the process in the same domain have the same view or not?
Okay.
I mean,
so I think I understand the question now. I think the question is whether all processes in the same domain have a consistent view, global view to the address space. The question is, the answer to that question is almost a no with a little bit qualification. So I think I want to answer that question a little bit later because a lot of this talk is talking about how the address space is set up, what is the process boundary, and how the isolation is achieved. And I think after we go through those slides, the answer will become clear. Okay.
Question.
Yes.
So at any point in the design space, was this sort of motivated by the processors that do not have these kind of isolations available? So they are these ARM processors that don't have virtual memory at all?
Nope. ARM, Intel, they all have virtual memory support. We actually do use virtual memory support, which I will get to very quickly. The design point is not about whether the hardware supports hardware isolation. The design point is how efficient can you move data among processes and how strong you can bring the isolation. Like I said, using hardware isolation, on the surface, you have very strong isolation between processes, but for performance reasons, all OS we have seen that use hardware isolation have to punch big holes to make the isolation weaker, right? So by using software isolation, even though you're not using the hardware feature to isolate processes, you don't have to punch any hole. You really maintain your principle. So when we say processes are strongly isolated from each other, what does that mean? I think one criteria really is we can kill a process at arbitrary instruction boundary without impact on other processes. That is how strong the isolation is. Each process has its own GC heap. They don't share GC heaps. They don't share objects on the GC heaps. So to answer your question, all the processes don't know what other processes are doing, right? Yeah. So this picture shows the overall system architecture. There's a microkernel in the bottom, and this microkernel, if you use Intel terminology, is running in run 0, is a supervisor mode. Everything else runs in user mode. And for each address space, the big square up there, for each address space, we call it a domain. And the domain is consist of a domain kernel and multiple processes on top of the domain kernel. The domain kernel, to be clear, runs in user mode. Is running 3 code, not supervisor mode code. So the responsibility of microkernel is, like I said, physical memory management, CPU scheduling of different domains, the lifetime management of domains, and inter-domain communication. The responsibility of domain kernel is CPU scheduling of processes, virtual memory management in the domain, the lifetime management of the processes, and inter-process communication. And in a later slide, you will show there's a bit more to it. There's shared heap in the domain kernel, which is critical to the whole thing. So we said each driver and each I/O service is a user mode process. What does that mean? So this is a picture shows the I/O pipeline of a typical web application. So the traffic arrives at the NIC driver, which is a process. Then there's an inter-process communication from the NIC driver and say, I know web server want to listen on port 80. This is port 80 traffic. I will just give it to the web server. So web server is a separate process. They all have their own GC heap. So web server then make a decision. It parse the request and see if this a static file content or it's a dynamic content. If it's static file content, I will talk to the file system directly. I don't need to bother the web app. I can talk to the file system directly. And file system will say, OK, somebody need to retrieve the content of the file. Do I have it in my cache? If it's in my cache, I can satisfy the request. If it's not in my cache, I need to talk to the disk driver, which is in yet another process, right? So you can see in this whole picture, to satisfy a file request, data have to traverse through multiple process boundaries. This says we better have efficient data transfer mechanism. Otherwise, the performance of the system will be unusable. And as a corollary, it also says the data must not live on the GC heap. Why? There are 2 reasons. Remember, processes have their own GC heaps. They don't share GC heap. So if the data live on a GC heap, when you transfer that data, you have to copy that data. And we all know copy kills performance. And in this picture, the copy happens in multiple levels, right? From disk driver to file system, from file system to either the web app or the web server, then to the NIC driver. There are multiple hops, multiple copies. It just completely unusable. Another thing is, if the data live on the GC heap, that means you are going to have a high churn of collections, garbage collections in the GC. For example, nowadays 10 gigabit networking is fairly common, right? Imagine you have a 10 gigabit network card and you want to saturate the wire. So in the NIC driver, if the data live on the GC heap, that says every second you need to collect 1 gigabyte of garbage. That's a lot. That you're writing a GC stress, not a real workload. So data must not live on the GC heap. So where do data live? The answer is the shared heap. So shared heap supports bulk transfer of data. Shared heap is implemented inside the domain kernel. So there's one shared heap per domain. Several characteristics of shared heap that's different from the GC. There's no object relocation. If the data is there, it's there. You don't relocate, not like GC. There is no typed objects. Everything is a byte, right? There's no object, there's no pointer, there's no reference. Which means if you need to transfer a graph of objects from one process to another, you have to serialize and deserialize. You have to serialize into a stream of bytes, put it on the shared heap, and deserialize on the other end. So you actually want to minimize doing that because it is copy and it also involves GC heap traffic. But there are certain things this is necessary. But there is actually also advantage, which is because of the serialization, you actually have versioning support by definition, right? The serialized format is your versioning format. And then you can actually have different representation on the GC heap, whatever you like. You can version that freely. Shared heap, even though the shared heap itself live in the kernel, we do have process level lifetime management and accounting. Meaning, if you allocate from the shared heap, it is charged to the process. So the kernel and the resource manager actually knows how many bytes you're using from the shared heap. And from there, we can make resource management decisions. Process level lifetime management in the sense that if the process allocates some shared heap memory and the process goes away, right, get terminated, then the process doesn't have to clean up the memory itself. It's actually taken care of by the kernel. Everything is clean. So the name shared heap implies the data can be shared. In fact, the data can be shared. Most of them are shared, but there are also the concept of exclusive data. So what is exclusive data? Exclusive data says I allocate from the shared heap, but I'm the only owner of that data. Because I have exclusive ownership, the content is immutable. I can change what it says, right? The other side is shared data, which says it can have multiple owners. Multiple processes can access the same data, but the content must be immutable. You cannot change the content. Because if you change, then you run into tons of issues. I have a separate slide talking about that. So a typical pattern using shared heap is I allocate a exclusive data. I put stuff in there. After I'm done mutating the content, I freeze it into shared data where it becomes immutable. Then I can freely share them, right? Yes?
How does one process tell another process that the data has been updated and it's available for reading?
The data is updated and is freely available.
I mean, how is synchronization among processes done is what I'm asking, I guess. Does it send a message?
Oh, yeah.
Okay.
So I will talk about the ownership transfer.
Yes, that's what I'm asking. Yeah.
Yes.
Okay, yeah.
Okay, good. The lifetime of the shared heap allocations are managed by handles, which is a kernel concept. And the construct is exposed to application code as a few data structures that I will talk about later. So we talk about shared heap. Shared data is a primary representation of a shared heap allocation. So what is it? It's a small GC heap object to manage the handle. Yes, go ahead.
The sharing is a domain call or an actual kernel?
I'm sorry?
The sharing of the whatever memory you create, is it a domain kernel call or?
The sharing, I will get to that. The sharing is an inter-process communication mechanism. It will need domain kernel's help. I have a slide to just talk about the transfer, handle transfer mechanism. Okay. So the shared data is a small GC heap object that wraps the handle, right? So the reason you want a GC heap object to wrap the handle is so that you can do data lifetime management. What you don't want to see is the traditional C++, C++ programming model where I can allocate, I can free, and I have the pointer. Even after free, I can try to use it, right? No, this kind of nonsense. It's managed by the GC heap object, which is both disposable and finalizable, which means if the application code cares about being fast and being lean, it can call dispose promptly after use. Or if it's I don't care, just a playful app I'm writing, I don't care about that, I just want to focus on my business logic, it can rely on finalization to clean up the data. Either way, you don't have the free use after free problem. I mentioned earlier the content is immutable. This is guaranteed by the system. There's no circumventing that rule. Shared data can be transferred across process boundaries very efficiently. I will talk about how. So this is the implementation of shared data. So at the top, you notice there are multiple segments So what it means is a shared data doesn't need to be a contiguous array of bytes. This is different from byte array, right? The reason we allow this kind of multi-segment data is there are many workloads where you want to do things like concatenation. I'll give you a few examples. One example is I have a payload I need to send out on the network. How do I do that? Right? I have a 1 megabyte payload. I want to chop it up into 1,500 bytes chunks. And then for each chunk, I need to append a header to it before I put it on the wire. So what do you do in that case? The 1 meg data you have may be contiguous. It doesn't matter. Let's pretend it's a single handle thing. So the handle is here. The descriptor here contains the offset and the length from the handle. So the handle here can be 1 megabyte, and the descriptor can say, I don't use 1 megabyte. I start at offset 0x100, and I have 100 byte length. That is totally fine. And the data above can only see that 100 bytes, not the entire 1 megabyte. And then you can start appending headers to this and make a multi-segment shared data, and you can put it on the wire. Right? So this is a handle I was talking about. So down below, this is a domain kernel, and the data structure down there is managed by the shared heap. We have a post-mortem finalization mechanism, so it's different from the CLR finalization. For post-mortem finalization, it requires a pair of objects. So there's a pre-mortem state and a post-mortem state. That's about it. So the shared data is just the region wrapping handle and multiple segments. How do you share a shared data? So this is the first example of sharing. I only have a single handle to the kernel. I only have a single region wrapping the handle. But I can actually have multiple descriptors wrapping the same handle. So why is this picture interesting? You can think about the audio editing case, right? How do you do audio editing? You have a tape. You say, I don't like that sentence. I want to cut off something. In a traditional mechanical way, you just get a scissor and glue. You cut, you throw away the middle part, and you glue the two parts together. You can do that here, right? Or you say, I really want to add something in between. You can do that here. So this is the first example of sharing. This is the second example of sharing. This says, on the left-hand side, I have a shared data. I can call clone on the shared data and get a different shared data here. And notice the clone doesn't do any kernel operation. It doesn't create new handles. It just uses multiple GC heap objects, reference the same region wrapper. And when you clone, you can specify offset and length. So the first shared data may be 1 megabyte. The second shared data may be half megabyte because you specify the offset and the length. The third picture shows how you share data across process boundaries. Right? So there's a kernel handle here, and actually there's a piece of data in the shared heap, and there are multiple kernel handles referencing the same data in the shared heap. And on the left side is one process. It wraps the handle. On the right-hand side is another process wrapping the handle. They reference the same data, but they have their own independent handles, which means down here you have to do ref counting. So you asked about the handle transfer mechanism of shared data. This shows how we transfer the handle. So we start with this process. It says, I have shared data, I have the handle, and I want to transfer to another process. What it does is it just uses a Midori IPC mechanism and send a message to that process. But when you send that message, the IPC library actually notices, this message is special because it has a kernel handle in it. I can't just copy this message in the user mode rim buffer without talking to the kernel, because that will mean this process will all of a sudden use this process handle table actually in the code. That's impossible. It's impossible for one process to use another process handle table. So it will just get some garbage and crash. So if the message is clean, right? It doesn't have handle, it's pure data, then it doesn't need kernel involvement. You just send it through the IPC channel in the rim buffer, the other process get it, demarshal it, everything is fine. If the message has kernel handles, then it actually goes through the kernel. When you let the other process know, hey, you have a message, that call actually goes through kernel. What kernel does is that it says, I notice in the message there is a kernel handle. So, and I know this is a transfer call. Therefore, I will kill this handle. This handle doesn't exist anymore. I will allocate a handle in the destination process handle table. And not only that, I will also modify the message so that the reference to the handle in the message now reference this handle. So this picture is similar. It says, I have shared data, but instead of ownership transfer, I want to share it. Meaning, I want to keep a copy, and I want to give a copy to the other guy. A typical scenario here is, if I'm a file system, someone asks me for the file content. I read the file content from the disk. Well, now I want to keep a copy in my cache, just in case someone else asks me for the same file. And I need to, of course, give the copy to the requester so that it can do its work, right? So in that case, it's a share, not a transfer. So in the share case, again, you put the handle in the message. The IPC library notice, the message has a handle in there. Therefore, I can't just do user mode thing. I have to call into kernel. Kernel says, okay, you have a handle in the message, and I know you are trying to share. Therefore, I will leave this handle alone. I will allocate a new handle in the destination process handle table. I will have to increment the ref count here, and I will change the message so that the message refers to this handle instead of this one. Then I'm done. I will let the other process know it has a message. When they read it, the handle is already there. Yes?
In that case, would you also have to make it immutable, the data in there?
Yes. So before this happens, the programming model already guarantees the data become immutable. So the way you do that is you allocate shared data, you change the content. After that, you kind of free the shared data, you free the exclusive data into shared data. You cannot send a shared data out. You can only freeze it into, you cannot send exclusive data out. You can only freeze it into shared data first, and then you can send it out. So when you change from exclusive data to shared data, the data becomes immutable. Nobody can change the content. Yes?
Yeah, in the transfer case that you had before, you don't actually change it to be immutable. You just give up ownership and then the other guy gets ownership? Or is it effectively just sharing that loses the original owner?
Right. So we decided not to do that special case. So even in the transfer case, we say you freeze it first and the receiver get a shared data, not a exclusive data. The reason we made that decision is sometimes if you are the origin of the data, you actually know it's exclusive. But sometimes you're just passing the data along, right? For example, file system again. File system gets the data from the disk driver. When it gets from the disk driver, it already lost exclusivity, right? The disk driver might keep a copy. You don't know. So we just say, okay, we want to make this simple and consistent. When you transfer, it's shared data, it's immutable, period. And we actually find it sounds like restrictive, limiting, but in real practice, when we build the system, we actually didn't run into any issue with this. Yes.
When you do the IPC, I assume you use IPC, right? It's IPC synchronization. It's a synchronization IPC or asynchronization IPC?
It's all asynchronous.
Asynchronous.
This is all asynchronous.
Because I was working for the L4 microkernel, and we were having a similar zero copy between drivers, right? We call all drivers for L4 is user space too. So and we were finding that the finally bottleneck becomes the IPC between the different small pieces.
Yes.
So is there any? I can ask later.
So in Midori, all IPC are asynchronous, and all IPCs are pairwise in the sense that if P talks to Q, they have a dedicated IPC ring buffer between them. Okay. There's also the concept of three-party handoff in the sense that if I have three processes, P talk to Q, talk to R, the final data need to get from P to R, but Q is in the middle. We can actually skip Q and establish channel between Q and P and R directly and push the data through that way.
And also not necessary for Midori, you don't go through the kernel, right?
Right. So as long as the message doesn't have handles, it doesn't go through the kernel at all. Right. It's just user mode rebuffer thing.
For L4, most IPC are synchronization, right?
That's right.
And
Yes.
So, so why did you choose immutability over, let's say, something like copy on write? I mean, it looks like this makes your job easy, but how easy does it make the programmer's job? Because if
It actually
if you want
makes
to modify
programmer's
the
job easier. I will get to that. I have a slide for that.
I have a question. Is there an explicit instruction in a process to receive a message from another process?
You can think of that as message loop,
Okay.
right? So if you want to receive something, basically you say, I implement a server,
Okay.
right? So the client will just invoke you. They invoke you by giving you messages. So the server implementation, basically, you can think of them as callbacks, right? I implement the server, I put the message there. When I get called, I don't know. When a client sends me a message, I get called.
But within a process, there could be multiple threads, quote unquote, or tasks. So there could be multiple callbacks executing at the same time?
Yes and no. So the Midori process model says by default, all processes are single-threaded.
Okay.
Again, you can think of that as a big message loop, right? Basically, it says I have a big message loop, and I keep looking for my incoming IPC channel. If there's a message, I dequeue it and start working on it. If the work is prompt in the sense that it doesn't need to invoke other IPC to get answers, it's just CPU instructions, then there will be nothing interleaving with that execution in the process.
Okay.
Right? But there will be a termination point of that prompt context because sometimes you need a piece of data from elsewhere to finish your work. In that case, you have to park your execution context, send a message to somebody else, wait for that to come back before resuming your execution context. However, when that execution context is parked, you can process another incoming IPC message and start another server work. That makes sense? So the interleaving happens at very explicit turn boundaries. Within a turn, there's no interleaving. It's single-threaded.
And the top-level message loop, when a message is dequeued, it knows which execution context to resume?
That's right.
Okay.
Yeah.
All right.
But the sender does not know anything, right?
What do you mean the sender?
The sender just when the sender send the information, what does the system guarantee? System just guarantee I will deliver you to the receiver, but I'm not sure when, right?
The system can't even guarantee you can deliver to the receiver because at the time you send, the receiver might have already been terminated.
Right, but system guarantee that after you return from send, your message get dequeued, right? Put in buffer.
Correct.
Okay.
When you call send and send is successful, then the message is there. Whether it's delivered or not, you will have to
You have to
wait
put
and
in
see.
if you do need synchronization, you do need. Okay, so if you want to, I assume that the system looks like if you want to do synchronization stuff between ping pong to process, you should choose. You don't use IPC, right? I'm not sure. Because if you use, I mean, if let's assume all of IPC are asynchronization.
Yes.
If I need your answer, which means I have to set the package and wait for your package come back, and you don't know, the system does not guarantee anything happen, right?
Right.
So, which means when you have a scenario which two processes want to communication quite closely, so you switch to another mechanism or not?
No, it's a unified mechanism. It's a single mechanism. What we found in general is we don't want to build multiple mechanisms to do the same thing. It's actually a beauty of the system. You have one way to do it, and we can optimize that one way very aggressively. We don't have to worry about other stuff.
I have a question.
Yes.
So can a process process multiple messages concurrently? Supposedly, if those are independent, so
Right. So it goes back to the single-threaded versus term boundary. So it's both yes and no. Okay. By default, a process cannot use multiple CPUs. By default, a process is single-threaded, which means at most it can use a single CPU. But if you are processing an incoming message and you need to wait for something else to happen, then you can park that execution context. And when you park it, you can process another incoming message.
but in some cases, I might just be able to process two messages in parallel if they're independent enough. So would I have to spawn multiple processes in this case? Or?
Right. So we have different level of parallelisms. We found when you're writing server applications, most of the time, what you really want is scale out to be multiple processes. The reason is if you do that kind of scale out, then the system is already architected to be scalable to multiple machines. If you scale within a process, then by definition, it's hard to scale out of the machine boundary, right? But we do have in-process parallelism support. There's safe parallelism in the sense that it's not open API. You can create a thread. You can wait on multiple objects. We don't have any of those APIs. Instead, what we do have is I have a task I know I can parallel. So I will call a parallel for, all right? Then the class library will decide how to distribute that among multiple processors, how to do the rendezvous, and aggregate the result together. Right. Go back to immutability. Only immutable data can be shared. So I think a person asked, what about copy on write? We decided not to do demand paging in the system. We also decided there's no kernel tricks to do things like copy on write. We actually found that a huge simplification for both kernel and for applications. There's no memory mapped files. There's no such thing that allow one process to write while the other process read from the same buffer. They simply don't exist. You can't write code that way. So it forces you to think about the problem and the solution differently. But we haven't found a single problem when we build this system where this doesn't work. Right? In every single case, we found it works and it works efficiently. In the traditional model where one process can write, another process can read, you have the time of check, time of use problem. Sometimes it's a security problem. Sometimes you burn a lot of CPU cycles on the cache coherency protocol because of the races and the cache transfer from one processor to another. None of this exists because you cannot share mutable data. So by definition, the system is very, very CPU cache friendly. I will talk about caching. It allows simple and efficient caching. Yes?
So can this be projected back to your domain picture and say like all the domains are, so all of these are running on a single CPU?
No.
That cannot be right.
By default, each process is running on a single CPU.
But the whole domain could be spanning the different number of processors that are.
Oh, absolutely. If you have 50 processes, you can use 50 CPU cores. Now, we have a problem with the programming model, which is, it's nice, we have a shared heap, we have handle transfer, but how do we access data on the shared heap, right? If you remember CLR, the class library, whenever you do any data, is all binary. Well, the reason is, well, that's only mechanism available, but also all the APIs are expressed in terms of binary, like TCP receive. Well, it gave you a binary, right? Encoding, it used binary. So how do we access data on the shared heap? So we introduce a concept called span in the programming model. This is integrated with the runtime and in some sense, even with the compiler. This gave us a consistent view or consistent data access to both data on the GC heap and the data on the shared heap. So this is the example, okay? The encoding library doesn't talk in the language of binary. It talks in the language of span. So if I have data on the GC heap, what do I do? Well, you get the binary on the GC heap, you get the span, and you pass the span in. You get it out. You can call the API, and you get the information you need. What if I have the data on the shared heap? Same thing. It doesn't matter where the data live. You get the span. You call the same API. There's no bifurcation of the implementation of the APIs. You get the information out. Right? So span gave us a consistent and unified data access mechanism. So when we write code, we use span everywhere in the system. And when we develop the class level APIs, especially the low-level APIs, a lot of them are expressed in spans. So I said it's completely unified. It's not actually completely unified. There is a difference. Remember, shared data can have multiple segments, whereas binary is always contiguous. So when you have a binary and you get span, it's guaranteed that the length of the span is identical to the length of the binary. When you have a shared data and you get the span, well, this could be the entire shared data, or it could be a small subset. So the API, the low-level API, have to deal with this kind of discontiguous multiple segment data thing. For example, in encoding, the encoder will actually maintain some internal state so that it says, there's a UTF-8 encoding, and there's one character encoded in 3 bytes. And you give me a span which terminated on the first byte. So I will actually remember something in my internal state. So you can call this multiple times and pass in the following spans. When you do that, I will remember there's a leftover byte, and I will concat it together with the 2 more bytes I received and give you that character. Right? So it does require some work in the low-level API implementation. There's no question about that. But in the higher level API, this problem largely disappears. You also notice when I say span, I'm using span of byte here, but up there I'm using span of t, which brings us to primitive structs. So you all know primitive types, right? Boolean, integer, double, float, char, but not strings, not objects on GC heap. So a primitive struct it can have other primitive structs, and it can have this kind of primitive types as its fields. What it cannot have is it cannot have references on objects on the GC heap, right? So if you have a primitive struct, you don't have to write serialization code yourself. We actually provide the low-level runtime feature so you can read and write the primitive primitive structs from using one call from any span of byte. So this is an example. If I have a T, which is a primitive type, then I have a span of byte, I can just read it out right here, single call. I can also write it. And also, I can cast it into a span of U, if I like. So here's a concrete example. ICMP is a network protocol. There's a header in ICMP protocol. In traditional OS, what you would write is I have this network packet, I will read an integer here, I will read a boolean there, kind of thing. Here, you just define a primitive struct. This is enum, which is primitive. You define the whole thing, and then you say read. Simple as that. You get the strongly typed struct, and then you can access the information in a programmatical way. Yes, question?
Because you have strong typing anyway, did you look at letting primitive structs point to other primitive structs?
Yes, you can not point to, you can contain other primitive structs.
I see.
Right? For example, there's nothing wrong with I have a bigger header which have this ICMP header in it. Right?
So it's the user level kernel writing in C#. It's writing in C++.
C#, everything is C#.
So how do you check? Like for our regex, we use like magic, right? So how do you check? Because I assume you want like kernel can change between types, right? But the user level cannot. Like some actions you are not allowed, like user process application do, right? Some actions you are allowed to do for the inside kernel, right?
So the question is that there's certain actions you want to do in kernel but not allow in user mode.
Like for example, you want to sometimes you finally you need to transfer something between the reference to some way you have to transfer the safe. You have boundary between safe and unsafe, right?
That's right.
And some part of kernel need to trade.
Yep.
Unsafe stuff like this binary stuff become a reference delivered to the user, to user, right?
Yes. And you actually told the answer. The boundary is the unsafe boundary, right? So in Midori, basically the policy is kernel can have unsafe code. There's a memory manager in there. It's managed virtual address space, regardless what it is. It's unsafe code.
The question is when you do your checking is in the compiler time checking or in the runtime checking?
It's compile time checking.
Okay, yeah, got it.
So if your code compiles and it doesn't have unsafe keyword, then you're allowed to run. If you need unsafe keyword, then we actually fail compilation, right? Yeah.
What goes on when you say data.read or data.write for shared data? How does it find like the segment where that offset is, and what runtime checks does it have to do?
Yes. So go back here. Here, if you have a span, which is always contiguous, when you read and write, there's no problem, right? Here, we do have a convenience wrapper on shared data that read. What it does, it says, usually the T is relatively small. So in average case, I can probably find it on a contiguous segment. So I optimize that case. But what if this is large or the segmentation is terrible and it's not on one contiguous segment? For in shared data case, the implementation actually does a copy behind the scene to give you the contiguous view and then read the header.
So does read always result in a copy? Do the bytes get copied?
Does read always result in copy? The answer is yes, with a qualification. So I said Midori code is all C#. It's not strict C#. It's a C# with some modification. So one of the modification is we allow ref return. Actually, in System C#, they allow similar concept. So in the ref return case, it's not a copy, but otherwise it's a copy. In this case, it's a copy.
So it type of the span is a copy?
No.
When,
When you get span here, it's not a copy. The data, like when you call here, the data still live in GC heap. There's no copy. And when you call here, the data still live on the shared heap. There's no copy. And the span itself is not a GC heap object. It's just live on the stack. Yeah, it's a struct live on the stack. There's no copy. So I will be introducing many concepts. I will introduce one more, which is a destructible resource. What is a destructible resource? So in C#, you have finalizable objects. The semantics of finalizer is once the object goes away, become unreachable, at some time in the future, which is not determined, the finalizer will run and you will clean up. I'm sure everybody who have written C++ code says it would be nice if I have the C++ destructor semantics instead of finalizer semantics. Well, there's pros and cons. If you want C++ destructor semantics, you need to make sure the object live on the stack, not the heap. Because if it's in the heap, then you will not get destructor semantics. So what we did is we created this between runtime and compiler cooperatively, created this destructible resource concept. What it means is it's allocated on the stack. Now the GC heap is not allowed to live on the heap, only the stack. Because it's stack only, suddenly we can the compiler can give you the destructor semantics. So it really is the scope of the code. The moment the stack allocated struct is out of the scope, the destructor gets called. So it is enforced by language and compiler. It all happens automatically. There's no finalization. There's no disposable, right? You're free of resource management concerns. So one example of using the destructible resource is shared multispan. Remember in the picture of shared data, in this picture, well, that's a class. It lives on the GC heap. And in many cases, you need it to live on the GC heap. For example, if you're a file system and you want to put this in the cache, well, the cache, for better or worse, is a GC heap concept. It has to live on the GC heap. But there are also plenty of workload where the data need to traverse through the code, but you don't need to keep the data, right? Network driver is a great example. Think about when the hardware gave you the data. What do you do with the data? You need to inspect the header, which we use the primitive struct and read, right? Then we can inspect the header. Once you inspect the header, you know where to dispatch that packet to. So there could be multiple applications listening on the same network card on different ports and everything. So once you inspect the header, you know where to put the packet. Then you don't want to keep the packet at all. You just want to throw the packet over the wall to the process, let it deal with it. So in this case, why do I need to create a GC heap garbage, right? So the shared heap class is a small wrapper, but it's still a GC heap allocation. What we found in Midori work basically is whenever you can reduce the GC heap allocation, well, you see a meaningful boost in your system performance. It's not surprising. You know, all the talk about just let garbage collector do its work and just allocate, imagining is free. Well, it's not free. It's far from free. Yeah.
Kind of an object on stack is you do need the programmer know that, or you do a disk analyze?
No, the programmer need to be explicit. Okay. Because for this one, you are not allowed to box onto the heap. Okay. If you try that, it's a compile error.
So they are not object. Okay.
They're not objects. Yeah, it's actually much stronger than just a struct, because for struct, you can still box it, right? For this one, if you try to box it, you get compile error.
Also, you cannot share it, also, all of this stuff.
So the shared multi-span is a very similar concept to shared data. It has these multiple segments, but it doesn't have a GC heap footprint. It's used to promptly shuffle data through your process without keeping it, right? So by doing that, we can save GC heap allocations, we can save the cycles in collection, and we improve performance. One more concept, stream. A stream is a potentially large sequence of bytes containing unstructured data. So think of shared data, right? Shared data is very similar to shared data in the sense that there's no pointer, there's no typed objects, it's just a stream of bytes. For a stream, there is a producer, and then there's a consumer. They can live in the same process, or there could be a process boundary. The producer and the consumer can live in different processes. An important characteristic of stream is there is flow control. So when you write something in the stream writer, when you write something, what you get, you get a back pressure token back. You can choose to ignore it. It's legal, right? It won't give you compile error. But if you ignore it, you will buffer data in your local process. And if you buffer too much, the system will say, I'm out of memory and you are responsible, I'm going to terminate you, right? What it won't do is it won't, you write, I gave it to the consumer, you write, I gave it to the consumer, and eventually consumer become too fat and get killed. That won't happen because of the flow control. So when you write and get the back pressure token back, it's actually in your own best interest to pay attention to the back pressure token so you don't produce too much. So stream is used to shuffle data around process boundaries. In many cases, when we use stream, it's long-lived, right? So you establish stream, then you can shuffle tons of shared data across, and the stream can live forever for the duration of the process lifetime. There are also examples where streams are short-lived. One example is in the web server workload. Both the request body and the response body are streams, even though in a typical request and response, it's relatively small. But you never know, right? Somebody could be uploading a file that's 1 terabyte. You never know. So for the potentially large thing, you have to marshal it as a stream. The benefit comparing stream and shared data is for shared data, if the shared data is 1 terabyte, then you really need to have 1 terabyte of physical memory available for it, because everything needs to be promptly available. For stream, you can shuffle 1 terabyte data through, but at any given moment, you might be using 10 megabytes of physical memory footprint, because a consumer can say, I got this 10 megabyte, I will do something, I'll free it because I don't need any more, right? So you think stream as a long-lived pipeline to shuffle data through.
Streams are single consumer only, one producer?
It's a single producer, single consumer. One more concept, shared data, soft reference, and the weak reference. These are used primarily in caches. The purpose of these guys is how do you effectively use most of your available physical memory for caching without running the system into auto memory. Remember, Midori doesn't do demand paging. So unlike Windows, where the memory manager and cache manager work hand in hand to manage file system cache, in Midori, if you ask data, it's promptly available, it's in physical memory, there's no paging for you, right? So in that world, we still want to use the majority of the physical memory for file system cache or other kind of caches. So what we do is we introduce a concept of weak reference and soft reference. The lifetime rules are relatively simple. If there's a shared data, which itself is a strong reference, then if there's a shared data, then regardless there's soft reference or weak reference, the data is alive, period. It's a strong reference. It will pin the data alive. What about weak? Weak says somebody else have to hold it alive. If there are no shared data or shared data soft reference, there's only weak reference, then the data will disappear. It's a deterministic behavior. The data will disappear. You will not have it anymore. What about soft? Soft is something in between. Soft says, if I have a soft reference and there's no strong reference, there's no shared data reference in it, then in average case, the data will be there, except when the system is close to run out of memory. In that case, the kernel is free to steal from you and make the data disappear. Make sense? So strong says it's always alive. Weak says if there's no strong or soft, weak says it will deterministically disappear. Soft says in average case, it will be there unless the kernel wants to steal it. In that case, it will disappear. Yes?
What's the purpose of weak?
I will show you. So we build the file system cache using the shared data cache. The shared data cache, the majority of the data is not in shared data. It's in shared data soft reference. Okay? Therefore, you can do resource management fairly effectively on the cache. So what you really want to do is, in average case, you don't want to steal. You want to cooperatively tell the cache, hey, I think I have tons of physical memory. You can use 10 gig. Go ahead. And then something else come along. You say, even though I have physical memory, I don't think you should use 10 gig. Why don't you reduce your footprint to 5 gig? When you do this kind of communication cooperatively, the cache can run its own eviction policy and decide the best way to throw away stuff and maintain its cache hit rate. But in case this kind of cooperative communication doesn't work, for example, you run SQL Server, and SQL Server, I need 20 gig right now, right? You don't have time to do this kind of a cooperative dance. Then what you do is you will preemptively steal from the cache, and the policy is simple, it's stupid, and the cache owner will have to suffer some consequence, but it will know something happened, so it will know to reduce its footprint. So we use this in the file system cache. What we found is effective. It's an effective way to replace demand paging and manage physical memory.
So are all of these concepts just exposed to the system level or also to the application?
Right. So the question is whether the concept is exposed to the application or only system level. I think it's something in between. Okay. So when I say something in between, what I mean is, for example, all this stuff, they're all public types. Application code can use them, but most application code don't. What they do use is this high-level cache class.
But the soft one looks obviously just for looks. If you do some prefetch or stuff, you put in cache and prepare. If you're lucky, right? Some guy build the reference.
Yes.
So it looks like if you allow application to use this concept, and then you how do you interpret what does this mean, right? So
yeah. Yep. So like I said, it is in advanced namespace. Most applications don't use them. Most of applications just use the cache here. But if you want to build your own cache, for example,
they're all over,
right, they're allowed to use it. So you asked why we use weak. We found it's beneficial to the system performance to allow front-end caches on top of the back-end caches. So an example is a web server. Remember in this slide, we talked about the data traffic pattern of the web server. The backend cache is in the file system. It maintains the policy of what data I want to keep, what data I want to evict. We also build a front-end cache in the web server, which says, I will put the weak references in this cache only. There's no strong reference, okay? So at the end of the day, file systems still have full control on what data is available in there and what data is out. This one is weak only. What it does is, if a request comes in and I look up in the weak cache, if the weak cache says I have a cache hit, then I get the weak handle. Of course, I can't do anything with the weak handle. The only thing I can do with the weak handle is redeem a strong handle before I can use the content, right? And of course, the redemption can fail because the data disappear, right? So if you can, the lookup is successful and the redemption is successful, then you actually have the data right here. You can return it to the client right away. There's no IPC going on in the rest of the system. If either the lookup is failed, or you look up the handle and the handle failed to redeem to a strong handle, only in that case, you need to go to the file system and say, you need to give me the data. And once I have the data, I will return it to my client, and meanwhile, I will transfer it into a weak handle and put in my weak cache. So this way, we actually can reduce tons of IPCs in the system. And we found this useful in web server. We found this useful in font cache in several places. Yes?
Can the holders of the stronger handles tell how many weak handles exist?
It cannot tell how many weak handles exist, but it does have information on how many cache hits are on the weak handle. So if I have a cache hit here, then that information is available to the backend cache.
Okay, so I can use that to manage.
Yes, you absolutely need that information. Otherwise, this guy can say, this file hadn't been hit in 3 hours. I'm going to evict it. But reality is, it has been hitting every second here. You just don't know, right? So that information definitely is necessary. So like I said, the front-end cache can reduce IPC traffic. It can reduce load on the backend cache process. And the web server is one of the examples where we use the front-end cache to do this dance. So I have been talking about all the mechanisms available in the system. And when we build the system, the number one goal really is security and reliability. And at the beginning, we said we need good enough performance. Performance is a secondary goal compared with security and reliability. But at the end, because of the architecture we built and because of the performance culture in the team, performance actually turned out to be great. So I'll show you a few results. This is the speech server performance comparison with Windows. So this is actually running in production, handling live traffic from customers running in OSD data center. On Windows, it's C++ Windows, about 400,000 lines of code. And on Midori, it's bit-to-bit compatible in the sense that all the recognition results given any incoming traffic is purely identical to the Windows code produced. And what we have here basically is, this is latency, so lower is better. So we have about 1/3 of Windows latency. And this is number of concurrent clients running here. So for Windows, once it's above 9, it actually go exponential and blows up. For Midori, we can go all the way to 27. So at 27 concurrent client, the latency is close to Windows code when it's running at 9 clients.
So
yes?
is the code is rewrite or is ported?
It's a combination of both. So 400,000 lines of code, we can't just say I'll look at the code and I'll write our own.
But the old code is in C# too.
The old code is C++.
Okay.
Right. So what we do is a multi-stage porting. We first port it to managed C++. Then we do some surgery to make it /pure. Then we translate into CLR C#. Then we do the Midori port to put our keyword on and make it Midori C#. And at the end, the Midori C# code is about 100,000 lines. So it's about 3x reduction in the number of lines of code. This is a different benchmark. This is a SpecWeb 2005. It's an industrial standard benchmark published by spec.org. The workload consists of 3 different workloads. Banking is kind of like an online banking website where you log in, you check your balance, you download your check image, you pay your bill, kind of thing. E-commerce is kind of like Amazon.com. You browse catalog, you go into the shopping cart, you pay. Support is a typical technical support website where you download the drivers, you search for documents, you download documents. It shows, so this is very, very I/O heavy, right? We use 2 10 gig NIC, and we actually can saturate the wire. The workload is very, very I/O heavy. We also have multiple SSDs sitting at the backend to keep the content. For this workload, you can see for some of them we are twice as fast as Windows. For some of them we're 17% faster, and the geometric mean we're 59% faster. And the last one is 10 gigabit networking performance. This is a macro benchmark. It's just I have 2 10 gigabit ports, and I want to saturate wire. How much CPU cycle do I need to use? On Windows, it depends on the workload. Sometimes it's a 2.5 CPU. Sometimes you actually need like 9 or 11 CPU cores just to saturate that wire. On Midori is less than a single CPU. So remember I said Midori processes are by default single-threaded, which means unless we use data parallelism, the driver process can't use multiple CPU cores. So that was a concern when we start building the 10 gigabit driver. We say, do we have enough CPU resource, running on a single core to saturate wire? Turns out it works fine, no problem.
So you write the stack from scratch?
Yeah, the network stack is written completely from scratch.
It's normal that not even network industry people just borrow the Linux but delete the whole driver part and build their user level stack from scratch and get very good performance.
Sure, but it also means you need the driver to live in the kernel.
All right, but yeah.
Which we don't allow. We put this stance on that no device drivers live in the kernel, which means no third-party code live in the kernel, right? I think it's a huge performance advantage when you say there's no third-party code running in the kernel. Also, the entire network stack is written in safe C# code. It's verifiably safe. So I think I'll do a security talk in a few months, but it's interesting. We did some security work before we went into production. So we did tons of network fuzzing. What we found is the network fuzzing did find a few bugs. If I remember correctly, we found 7 bugs in our networking implementation, including web server and the TCP, IP, and the NIC driver. And all 7 bugs were either performance problems where when we're not the request has weird shape and we weren't paying attention and the system slowed down quite a bit, or they're denial of service where we weren't paying attention and the process crashed. One of the example is the content length header. Right? So in Midori, all integer arithmetics are checked by default. If you add 2 integers together, they overflow. boom, the process crash. You can't even catch it, right? It's not the exception you can catch. It's a process crash, deterministic process crash, and we did have that crash. So all bugs are either performance or denial of service. There's not a single bug that can lead to remote execution or buffer overrun, because when you write your entire stack, so the entire TCP, IP, the entire NIC driver, the entire web server, all the web apps, they're all safe C# code. So buffer overrun, remote execution, they just don't exist. Yes?
Question with the single CPU number. So do you know the percentage terms? Like was it 80% of the CPU, 90% of the CPU, or something? Can you tell? I mean, you can probably get the measure.
The answer depends on the size of the data. When the data is reasonably big, like 16K, we use less than half of a CPU core to saturate bidirectional wire.
This one's really not CPU. I mean, I did the same. So why I said that is because I was doing this on Atom. We do build a device which we try to test the bandwidth of Ethernet. So you just need a small Atom CPU and you can 10 gigabits is easy. But the whole part is there is the Windows cannot run that because you do go through the abstractions that was slow. So if you can, let's assume if you write your whole stack by yourself inside kernel, you can do the same thing, right? But here's the point is that in user level,
But for example, you have kernel mode web server, right? So is it fair to say that Windows could also achieve this by putting the components in the kernel mode? It will be hella unsafe, but heck, for performance, why not?
Well, remember, on Windows, HTTP, SSL, they're all in kernel. They're all in kernel.
On Windows, you cannot do this because on Windows, you are not all. I mean, how I did on Linux is we bypassed the whole stack. We basically the same things. What we did is just Ethernet get interrupted, we jump to user level, right? We carefully then we process all of the stuff in user level. There's no security, right? Because we try to make the speed, which means if you want to make the network device fast, you have to bypass the whole network layers. On Windows, you are not allowed to do that, right?
Well, the same way you do in Linux. You just write a device driver that pops everything
right,
out.
sure, but for normal situation, you are not. I mean, you don't have a code. So, and you in the Windows, you are not allowed to directly receive the message from driver. From
write your own driver to do it. You certainly can. But
I was just trying to get the sense of why is it taking, let's say, 2 CPU cores? Is it because of the user kernel process, the boundary switch that is still that expensive? Because there has been a lot of work in Windows to push things into kernel for this specific reason. And web server, let's shove it down. SSL, let's push it down. So everything goes into the kernel. And even if that isn't solving this, then there is something fundamentally broken. I was just trying to get the sense of where this performance is coming from.
Right. So there are a few reasons why it's hard for Windows to achieve the performance. One is if you have data in user mode and you need to send or receive, zero copy is hard because of a security concern, right? Can the kernel use user data buffer without paying attention to security, right? If you say, I don't want that, I want to protect kernel, then you have to copy. Or you have to say, I have to log the buffer, which also have its own overhead. Another reason is in Windows, the code path length, even in kernel, is horribly long. And then how you manage the data ownership transfer is also a problem.
So single copy I/O, according to you, contributes to a lot of the performance.
Right. So in this workload, actually, it really is zero copy I/O, because for example, when you download static content, the CPU don't need to touch the data at all. The data is DMA'd from the NIC driver in, and it's DMA out from the NIC driver. Right? The CPU don't need to touch the data. The CPU only need to touch the metadata that describe the data. It really is
This
zero.
macro benchmark just a send file?
Hmm?
The macro benchmark you showed just a simple send file. I mean, for the static.
This micro benchmark is not sending file. It's the content just live in memory.
No, I mean that if in Linux there's a send file, you can directly. It's basically zero copy. You can,
Yeah.
This one is similar.
Actually, this one is for both banking and support. There's tons of file download. For support, it's a large file download, and for banking, it's small file download.
That once you go to user level and send
Yeah.
through socket.
Yep. Okay, so that's the talk. Like I said, there's a series. We will try to do it once a month. The coming topics include network stack, storage stack, kernel, security, and a bunch of other things. So pay attention to the announcement, and thank you for coming.